Hello everyone. Today we're going to be doing a limits and continuity FRQ, and let's get right into it. Let f be the function defined by f of x is equal to these four functions over these four domains. Problem A. Find the limit as x approaches to 2 of f of x. Show the work that leads to your answer. So firstly, we need to find the limit as x approaches to 2 from the negative side of f of x. Now, the function that we'll look at, since this is a piecewise function, we'll be looking at this domain right here. We're looking at this domain because x is always less than 2 over this domain, meaning as x approaches 2, it approaches 2 from the negative side, from the left side, meaning we're going to be looking at this function for this first limit. Now, if we just input 2 here, we will get this expression, which equals 0 over 0. Now, 0 over 0 is an unacceptable answer. College Board will not accept this value as the value of a limit. So what we have to do is we have to say that this limit is of the form 0 over 0, and this allows us to now simplify the function that we're working with. So now we go here and let's just rewrite the function. And we can actually simplify this because this top numerator factors out to x plus 3 times x minus 2 over x minus 2. So this is just x plus 3. And since we're doing the limit as x approaches to 2 from the negative side, this will just be 5 because 2 plus 3 is 5. So we've found one limit. I'll delete my work here because there's not a lot of space. So this limit is 5. Now we have to find the limit as x approaches to 2 from the positive side. And instead of looking at this first function, we'll be looking at this third function and this domain because x is constantly greater than 2 in this third domain here, which means that as x approaches 2, it's approaching 2 from the positive or the right side, meaning we're looking at this third function right here. And this function is nothing special. We can just input 2 here and get our answer of 5. So this limit is also equal to 5. And when the limits from both sides are equal, that means that the limit as x approaches to that value is firstly real, it exists, and secondly, it equals to whatever the two limits equals to. So in this case, since both this is 5 and this is 5, that means that the limit as x approaches to 2 is also 5. And to say this and say this in writing, we have to say limit x approaches to 2 is equal to x approaches to 2 from the positive side. Therefore, the limit as x approaches to 2 is 5. And we have to say 5 here. 5 is equal to the limit as x approaches to 2 from the negative side, which is also equal to the limit as x approaches 2 from the positive side. So overall, it's equal to 5. Problem B. Is f continuous at x equals 2? Justify your answer using the definition of continuity. If f is not continuous at x equals 2, classify the discontinuity. So firstly, when we're classifying when we're trying to tell if f is continuous, if a function is continuous at a point, we need to make sure that the limit as x approaches to that value of the function is real, it exists, and if it's equal to that actual value. So what I mean by this is we need to check if the limit as x approaches to, let's say, a, has to be equal to f of a. So essentially in problem B, we're checking if limit x approaches to 2 is equal to f of 2. Okay, we have just found what this value is. This value is just 5. So we just have to check, is f of 2 equal to 5? Now, f of 2, finding this is very simple. We look here that f of x is equal to 3 when x is equal to 2. That means that f of 2 is equal to 3. Now we have this strange thing where 3 is equal to 5. This is obviously wrong because 3 is not equal to 5. And what this means is the limit is approaching to some value, but the function is not defined at that point. So what this looks like on a graph is, let's say this is the point 2, and this is 3, and this is 5. Now, the actual function could be approaching here, like this, where both the positive and the negative limits are going to be equal to 5, but the function is actually equal to 3. So we have this kind of open hole in this function. This isn't necessarily the function, but this is just a representation of what's going on. And we have that the actual value is lower or not, there's a discontinuity. And we actually have to say that we have to first answer if is f continuous, and we say that limit x approaches to 2 is not equal to f of 2. Therefore, f is not continuous at x equals 2. And since the limit, well, it's the same truth, because this is something called a removable discontinuity, where you have an open kind of hole there inside of the function, and the function is not defined at this point. It's defined at somewhere else. And this is actually true whenever the limit of something exists. Let's say that this exists, right? This value exists, but it's not equal to what the function actually is at that value. And this will always be a removable discontinuity. This will always be a removable discontinuity. And that's a helpful fact to know. So, problem C. Find the limit as x approaches to 5 from the negative side of f of x and the limit as x approaches to 5 from the positive side of f of x. Does the limit x approaches to 5 exist? Is f continuous at x equals 5? Justify your answer and classify any discontinuity. So we're actually told what limits we have to find. So to find this first limit, we have to check what domain this fits. So 5 from the negative side. So we'll be looking at this domain because x is approaching to 5 from the negative side or from the left. That means we'll be looking at this function, and we can just input 5 in here. 5, this is 2. And the limit as x approaches to 5 from the positive side, we're going to be looking at this function now, this domain and this function, which is going to be, if we input 5 plus 1. And we actually get something very interesting here. When there's a 0 with a kind of, when you're solving a limit and you get a 0 on the bottom, you have to check what sign it has. In this case, 5, right here, right, the actual function is 4 over x minus 5 plus 1. And x is approaching to 5 from the positive side, meaning x is always going to be greater than 5. X is approaching 5 from the right side. X is always greater than 5. Meaning that this value, so something greater than 5 is always going to be positive, right? Something going to be 5, greater than 5, minus 5 is always going to be positive, but it's going to be approaching 0. So if something is 0 and it's approaching 0 from the positive side, we have this is actually equal to positive infinity. Okay? So this is equal to positive infinity, and we can't say that the limit is equal to positive infinity. We cannot say this. College Board won't accept it, and it's not the right syntax. So the correct way to format this is limit x approaches to 5 from the positive side of f of x does not exist, comma, positive infinity. And we have found two of the limits. Now, the third part is, does the limit as x approaches to 5 exist? Well, we need to check if these two limits are the same right here. And clearly, these two limits are not the same. 2 is not equal to positive infinity. Therefore, this is not true, and therefore, the limit as x approaches to 5 of f of x does not exist. And we can delete this work here just to free up some space. And finally, is f continuous at x equals 5? So if we're proving continuity, then we have to check if the limit as x approaches to 5 is equal to f of 5. Well, f of 5 is going to be in this domain, so we're looking here, and f of 5 will just be 2. So we're checking if this is equal to 2. Obviously, this is not equal to true. You can't have something that doesn't exist equal to something that does exist. So this is not true. So let me just replace this with f of 5. Therefore, f is not continuous at x equals 5. And we need to classify any discontinuity. Whenever there is a limit that approaches either positive or negative infinity, there is an infinite discontinuity. It's just guaranteed. If there's at least one limit that is approaching to positive or negative infinity, it is an infinite discontinuity. All right, problem D. Find the limit as x approaches to infinity of f of x. What does this value tell you about the graph of y equals f of x? Now, the limit as x approaches to infinity of f of x, we're going to be looking at, let's erase this. We're going to be looking at this domain right here, meaning we're looking at this function, and this is the function right here, 5 plus 1. Now, if this x is approaching infinity, right? This is approaching infinity. If you think about it, infinity minus 5, right? This infinity minus 5. Infinity is infinity. It's very big. 5 doesn't do anything to the value of infinity, meaning this is just equal to 4 over infinity plus 1. And if you think about it, when the denominator increases, so you have 4 over 4, then you have 4 over 8, 4 over 100. Whenever this denominator increases, then this value becomes smaller and smaller. Now think about what happens when this denominator becomes the largest thing that could possibly exist, which is infinity. This approaches to 0. Since this is still inside a limit, this approaches to 0. So this is actually just 0 plus 1, or 1, right? So we have that the limit as x approaches to infinity of f of x is equal to 1. And what does this tell us about the graph of y equals f of x? Well, let's just graph something. This is 1. And this isn't necessarily, you don't necessarily need to graph the function in order to solve this. But to understand, if as x increases, f of x is going to approach 1, meaning that as we keep going this way, the function is going to keep wanting to touch y equals 1, but it will never touch y equals 1, meaning we have a horizontal asymptote here at y equals 1. Therefore, this value actually tells us that f of x has a horizontal asymptote at y equals 1. And let's go to the last question. Use the intermediate value theorem to justify why there exists a value c in the interval 3, 5, such that f of c is equal to 3. Be sure to verify the conditions of the theorem are met. Now, there are 4 steps when trying to use the intermediate value theorem. The first step is to define a function, f of x. Well, luckily for us, the function name is f of x, so we don't have to realistically do anything in this step, so we can erase this part. The second step is to prove that whatever function we are using is continuous on the interval. So we need to prove that f of x is continuous on this interval. So is it continuous? Well, let's check what the actual function is. So in the interval 3, 5, you can think about this as 2, 5, right? 3, 3, 5 is always going to be inside of 2, 5, meaning that this domain is going to be inside this domain, which is governed by this function, minus x plus 7. So we're looking at minus x plus 7 as our function. And minus x plus 7 is linear. This is linear, okay? And since it's linear, it's continuous everywhere. When you think about any linear equation, when you think about its graph, it's a straight line. And no matter what you do with this line, it can go like this, it can go like this, right? No matter what you do with the line, it's always going to be continuous. And more importantly, it's always going to be continuous everywhere, meaning that f of x is continuous on 3, 5. So that's the second step done. The third step is to check what the values of the endpoints are when you plug them into the function. So we need to find what f of 3 is and what f of 5 is. F of 3 is going to be minus 3 plus 7, which is 4. And f of 5 is minus 5 plus 7, or 2. Okay, now f of c, we need to prove that there's some c where f of c is 3. Okay, 3. When you think about this, what these two mean right here, when you're thinking about 3 and 5 here, we know that f of 3 is going to be 4, and f of 5 is going to be 2. Now, we know that it's continuous between these 2 points, but we don't know what the graph looks like. It's okay, we don't need to know what the graph looks like. We need to prove that some value of c is equal to 3 here. And 3 is going to be on this imaginary line. This is 3. Since the graph of the function is going to be continuous, there's going to be an intersection here, okay? And how do we actually show this in our writing? So we're going to show this by saying that f of 3 equals 4 is greater than 3, which we're trying to prove is inside, and the endpoints is greater than 2, which is equal to f of 5. Now, this statement is obviously true This is correct, but we're not done yet. We need to explicitly say that this statement is true. So since f of 3 is equal to 4, which is greater than 3, greater than 2 is equal to f of 5, is true, we cannot abbreviate, so we need to say the intermediate value theorem guarantees a solution to f of c is equal to 3 such that c is on 3, 5. Okay, and there we have it. Using the intermediate value theorem, we've proved that there has to be some value f of c equals 3 on the interval 3, 5. Now, let's double check our work. Now, the answer to question A, the limit as x approaches to 2 is equal to 5. We got that right here. Question B, f is not continuous at x equals 2, and this is a removable discontinuity, not continuous, meaning that our answer here is also correct, not continuous and removable discontinuity. Problem C, we have limit as x approaches to 5 does not exist, f is not continuous, and infinite discontinuity, vertical asymptote. They asked to classify the discontinuity, so infinite discontinuity is correct. It does not exist, it approaches positive infinity, and it's not continuous. Does not exist. And problem D, this is equal to 1 right here. This means that y equals 1 is a horizontal asymptote. Cool. That's exactly what we said here. And lastly, problem E, on the closed interval 3, 5, f is, I think this is open interval, but it doesn't really matter. F is entirely given by this. This is linear, continuous everywhere. F is continuous. We wrote that. And since basically what we wrote, the IVT guarantees that there is some C, so guarantees some C there, and we got that right here. Okay, thank you thank you everyone for watching. I'll see you next time. Goodbye.